Hello. I'm very happy I can give this mini course. This is very introductory course to some in all mathematics. As you know, mathematics is just investigation of invariant groups. This is just the case. I would like to tell you about the new invariant, new discoveries of invariant in affine geometry. Yeah. So in affine geometry, you know, affine transformations. These are just linear transformations with translations, which are defined by if you have I is equal to a matrix B. So that's transformation. This is a matrix which is we transform the coordinates of the point into another coordinate in translation. So that's affine invariance according to these transformations. Only there is only assumption that this matrix is invertible, no any assumption. And then, the invariants of such transformations are very important because they are connected with vision, with looking on some. If you look on some structures, then, for example, in move from other perspective, then some configurations are preserved. For example, parallelity is preserved, or center of the interval is preserved. So this is very important that sometimes if you have, for example, some symmetric structures, some properties of symmetric properties, then they are preserved. Well, doesn't matter on which side you are looking on. This is not the projective geometry. This is affine geometry. In projective, of course, you look to the infinity. Here there's infinity, but not like in projective geometry. So this is, and then you see the idea is very simple in some sense, because if you look on the cycle has the center of the cycle. That means that if you take the point here on the cycle, then you reflect it according to that point to another point in the cycle. So the center is something like the point of reflection of a symmetric. This is a center of symmetry, we call it. The center of symmetry for the cycle. And yeah, but if you perturb slightly the cycle, but even if you have the cycle, if you perturb a bit the cycle, then there is no such point. Yeah, no such point that each point of the cycle are symmetric according to him or something to the another point. You understand? So if you have questions, we can maybe. But this is now it's simple, so I will tell also slowly. And you see, then the construction is very natural, which is also does depend on the transformation, affine transformation. Of the center does depend on affine transformation. Of course, if you transform the cycle affinely, then you get ellipse or something like that, but always with the center of symmetry. Always will be this point, center of symmetry. It's not disappearing, of course. But if you perturb cycle, then of course no this center of symmetry. So how to but the question is natural. Is then anything left? Because we see sometimes something which is very close to the cycle, but it's not cycle. So then it should be some measure of symmetry and some geometrical kind of response for this perturbation. So how the construction is going on? You see that you can take any point inside the figure. It's a figure inside the figure here. P. You take the point, and if this is the more dimensional figure, then it's so that then you of course put through this point some hyperplane. But if this is the plane, like here, you take this line, and then you have a perpendicular red interval, and this interval is perpendicular, is divided into two parts, T and S. And if you to this parallel tangent to the figure, this parallel lines. So if you move this line a bit, then of course those also move, and also this interval moves. And sometimes, and you see how it is changing. The length of this T and S is changing. For example, if you take this direction, then this part is short, this is long. Here are almost very similar. So if you go around the point, around this point, then you get such function. The f of the according to this direction on P, but P is not here, it's somewhere. Then you get a function which has two non-degenerate critical points, maximum and minimum. Well, you can easily figure out by yourself. I mean, this is trivial. If you go around, then this sometimes this is smaller, this is big, longer, and then opposite. Get some minimum, then get some maximum. But there is only one point where this function is all the time constant. Of course, the center of symmetry. Because if P is here, then doesn't matter what parallel lines you take, always this number is 1. Yeah, it's always 1. So then what does it mean? That means that all points are infinitely critical points. So the center of this symmetry as a point is infinitely degenerated point, extremely unstable, degenerated. So if you perturb, but this is cycle, 4 cycles. So any other point, we have such picture. And then nothing else. That's nothing else. We have only line and points which are usual non-degenerate critical points, minimum and maximum. Non-degenerated means that the first derivative at such point is vanishing, but the second not. Okay, then this function, of course, has some properties. If it's a more dimensional situation than the sphere, for example, or the set, so then we have directions. This is sphere n-1 dimensional. This is just the internal part of the oval. And there's a property that if you of course differentiate according to this point, then it is constant on that. This function is constant, of course, on this plane. And there's such property which is very convenient if you calculate this function in more dimensional situation. And then look, then this situation is different if you have perturbed. If you have perturbed, it's not cycle anymore, but something, then you define some set sigma of such point, you find such point P, where exists such direction, this is here, such direction that that this function T over S has degenerated critical point. Degenerated critical point. Degenerated critical point. I will give next course the. So this is non-degenerated critical point, and this is degenerated critical point. And of course, higher that no, but here higher here numbers gives high degeneration. So so if the function f on phi has, which is one dimensional, has somewhere phi to power 3 or more, then we put point. We just mark the point. Yeah, and it appears like this. And this is called bifurcation set in some sense. If you, but maybe this is too early, but to say about it. But so you see, why you can ask why you take these parallel lines. I take parallel lines because they are affine invariant. If something is parallel, it's invariant. So everything is affine invariant. So if I look from other side or change the coordinates affinely, then I have the same number of sharp points. I have the same structure. Nothing is changing. At least not important things are not changing. So this set will have the same structure. So this is why this construction is so important. You can make any constructions, but maybe you construct something which disappears if you change variables. Okay, so this is just the definition. You see, the definition is that this is special set is invisible. Normally, it's invisible. So yeah. Yes. So you might, if you prefer, you can take 5. You can take 5. Yeah. But because this is the function of p is constant in some sense. You fix it, and then you have function only on the angle. You go around. It appears that there is one point phi where for which this function has degenerate critical point. So there's first derivative in that point is 0 and second derivative is 0. But of course, it might be third 0, fourth 0, and so on. In fact, in such points, these sharp points cost, then even third derivative is 0. But fourth derivative is not 0. Okay, but I hope it's easy to okay. And then another construction of this set is maybe even easier, because the construction is by just you take chords, intervals, joining the tangent points of these parallel lines or parallel lines. I took only 2 here, but you can take all parallel lines. So for example, this curve. They are taken all parallel lines, and then you have envelope of these lines. It appears that this set is an envelope of that lines, and this is affine invariant construction. I go there. So there are some examples of such sets. You see, it depends on why this is so important. I tell you in a moment. But you see, this is kind of shape of the oval. This is the oval figure. This is always, if you take 2 points inside, then it's always inside. Yeah, this oval. There has no inflection points. So you see how complicated symmetry is here. This is calculated by the program. Then so complicated. Also here, well, here is less complicated. The previous one the previous one was not very complicated, you see? But because it is almost cycle. So there are something here, something maybe here, something maybe here, invisible normally, but visible by this function. So this is just what we need in science, to see invisible. Of course, invisible by eyes and so on, but visible by our mind. This is for our mind, it's easy. Okay, so some other examples. Now I show you the construction of some dual object to this set. This set is called center symmetry set because center symmetry is a point. Yeah, if you perturb it, then there's no point anymore, but the set. This set has a bit different properties because point is infinitely degenerated, but this center symmetry set points are finitely degenerated. But doesn't matter, they exist and they are very important. And then you see, if you take the curves, this is the initial curve. If you take the curves which are moving after some time from that curve, then after some time they have singularity starting, and they are moving on that blue center symmetry set. And this is, in this point, is maybe similar to optical problem where wavefront is moving, singularities of wavefront are moving on caustics. But there's no, because this is not caustic, and also this is not wavefront. This is not the distance. The distance here is not metric distance. I show you in a moment definition. So the definition of this black set as a dual of that set is just you take this from the beginning, this Z, and then you take the interval, you see, between two parallel lines, A and B, are points of the parallel pair. So then you have this parallel pair of lines, and you take the point of the between these lines, or lambda 8, just between on the distance of lambda, but on the chord joining the point. So there's no, we have no any metric here, only intervals. And of course, with interval we can divide into, like here, in the form of lambda. Lambda is less than 1, greater than 0. So this is called, in fact, Wigner didn't introduce it, but because he mentioned some problems like that, so this is called Wigner caustic, but we call it Wigner caustic, but it's better to say it's a Berry caustic. Michael Berry, who is the often visitor of the Yahoo Center, but in some sense we have to discuss it. So Wigner caustic is something, it's a dual for lambda equal 1/2. 1/2 is very special. So there's a distance. You see distance, you make this and then finally the lowest one. The lowest one is that one. Okay, this is shown that this is jumping and gluing together this thing. And this is the dual. We call it Wigner caustic. And then yeah, let me define this about this Wigner caustic, because we should have something about affine equidistant. Equidistance is a equal distance. Yeah, equal distance. So, for example, if you have the, like in the wavefront is usually done, then there are directions which are orthogonal, so you have inner product, and then this is the wavefront is moving like that. That the distance here is, say, 1 second. This 1 second, if the speed of light is c, is some distance. So this is equidistant. wavefront is moving like that, and then you have caustic, yeah. But here we have no orthogonality. Just in this geometry, is if that is, you can say that sometimes something is orthogonal to something, but it is not preserved. It's not invariant. So, so we have now we define this equidistant, which is something different than the usual equidistance with metric. So M is closed submanifold of some affine RQ. Affine space, this is something like Euclidean, but in the chart. So you put the chart of which are Euclidean, but the object has no any distinguished point. Euclidean space has 0, for example. I mean, not Euclidean, but the vector space has 0. Not also Euclidean as a vector space of 0. Okay, and then translation is defined translation. Yeah, very trivial, very trivial. We take two, you see, 2 points of BFM. We can add this because this is affine space. So we can just take differences of points, which are vectors. And then you see we translate x into x plus something, which gives another point. This is translation by that. And the pair of points is called belonging to M. It's called weakly parallel because this might be many dimensional. For example, you see if you have in 3 dimensions, then if you have in 2 dimensions, if you have the surface, then at 2 points you have the tangent lines, tangent planes to say to some 2-dimensional surface in R3. Then these planes might be parallel or not parallel. And that's it. There are no other possibility. But if you have, this is in R3. In R4, that's different. If you have 2-dimensional surface, then 2 lines, 2-dimensional 2 planes might be completely parallel. So then so this is all vectors here are the same like here, vectors. It might have intersection like that along the 1-dimensional along the 1-dimensional line, and also completely only having common point. There are 3 possibilities. So it's difficult to draw this picture. Some people like to draw it like that or something. So the 2 planes in R4, 2-dimensional planes, can have generically only common point. So this is the parallelity, you see. So this are parallel, weakly parallel, because there is 1 dimension where they are not parallel, but in other dimension they are parallel. This is only in dimension more than 3. In 3 dimensions, there is no such graduation of parallelity. It's only parallel or not parallel. Something parallel, you understand. Like on the lines on the plane, they might be parallel or intersecting. So not parallel. But lines in theta in space, so that's more possibilities. Even I cannot intersect. Okay. So it's weakly parallel. And then this is just a simple definition of this, or writing formally how it looks like. Let's see if you take the painted plane to M at alpha and then in beta, and you translate it to alpha, then this is just giving the something which is not the whole space. And then K is K. This is because it's K parallel. If this thing is just exactly dimension of that space is K. So maximally parallel is if this is K is equal Q. If but this is called okay, but this is called this is not different. K Q here Q is N. So well, N is equal the dimension of M. So then we have two N dimension. If K is equal N, then this is strongly parallel. If K is equal N, this is strongly parallel. This is very small. Yeah. K bigger than N, so this is just K parallel. And so this is just that a very simple notion. And then the interval passing through alpha and beta is such line. You see, we write. This is usually we write the interval using some parameter lambda, then 1 minus lambda times another coordinate, and then these are all points on the interval. That's we remember from school. And now an affine lambda equidistance of M. What is this? So that what is this? What is this? But which is not Euclidean equidistance, but affine equidistance. These are all points in this affine space that they are just what some fixed lambda. This is lambda is fixed. That's weakly parallel. You know, if alpha and alpha beta belongs to M are weakly parallel. If they alpha and beta are weakly parallel, then these points form this just the equidistant in general in all dimensions. But on the plane, then this is just exactly also this weakly parallel means parallel. Only that's difference. And here on this definition, we have this just we define for lambda equal half of half one of the two. We call it Wigner Kosti. And and then just to complete this calculation, which is very elementary calculation. So we take this transformation of intervals. You see, we consider the tangent space to this affine space, and then transform to the just Cartesian product of RQ and times RQ, but it's a coordinates of that. And chord transformation, lambda chord transformation is just a transformation. You know, take 2 points into another 2 coordinates into another coordinates like that. So x plus x minus, x is defined by x plus x minus like that, and x dot is defined like that, x plus minus x minus. And this is very, this is linear diffeomorphism, very simple thing. And we take our ovals, our space M product is just contained in this product of this affine space. And it appears that if we take the image of this product in the space, just on the space x dot, then this caustic, Wigner caustic, is the set of critical values of the projection in the tangent boundary. So this is just the formal, very nice recognition of this Wigner caustic. Yeah. And some examples of Wigner caustic. Wigner caustic is a bit different. You see, this is dual to center symmetry set. You see, if this is flat, this is flat, this is flat, and in some sense, this cusps, this sharp or is that going in that where this is flat. And that's also here, if you look. This one, well, you know, that's not, this one is maybe here, maybe here. That's not yet, you know, defined which one, what kind of shape properties, cabbage or something. For some symmetry set, we know more or less, but for that, no. And then why this is so important? If you consider the organization of molecules, molecules are, sometimes they have, say, boundaries, kind of. There is a, you know, well-defined surface, which is distribution one cell to another cell, you know, where inside is everything is defined. And the packing of spheres or the packing of some ovals is just exactly our nature is built of. So you see that shape, but the shape need not be visible. You know, this shape need not be visible. Sometimes this is only interaction, not shape, not the boundary. And then there is this shape has this center symmetry. And it is, and how complicated it is, says about the complication of the structure of the, in this picture, the complication of the structure of the boundary. But in fact, no, it says about the complication of all the structure of the molecule. And why this is important? Because it depends how it looks like on its boundary. It depends how it attached to others. So the complex system, how is a complex system is built up or made of people. Now people are different, you know. Some people have a few properties. Is nice, is smiling, and very sport person. Another one is only smiling and has no. And then, of course, there is something in common. Something in common, then interaction is here. Oh, you see? Something in common. Something in common. That's, of course, here is empty. Some properties are empty. I mean, no responding molecule or object to which my attach, interact. So this is a quite new method, not finished yet. I mean, for the theory to so build the chains and some and understand coagulation of some objects in our structure in nature for complex systems. But here, this is a method to use the kind of interactions through the invisible shape of something like a boundary. But this is not a boundary. It will not be very visible. Only interaction. So then we can, if you take off these red lines, then you get some strange picture. You get only this yellow points, and then the sets, and then connected by them. And this is just exactly, these are centers of some objects, and this one is interaction. Different interaction. Not like interaction of electromagnetic waves. That's, of course, because if you look on this attachment, this is by shape, interaction by shape. Yeah, by shape of the boundary. That's what then. Oh, not very similar, in fact. Yes, because you see, this is sometimes flat, more flat, less flat. You know, this is more curved. This is, and then this in here is less visible than here. But here is very visible. So then if you have, for example, two bodies like that, this body and that body, then of course, then they prefer to be attached like that. Not like, for example, that. You see, this. The tangency, I mean, the adjacency of these shapes here is much more, I mean, degenerated than this one. They have very much in common. You understand? Yeah. 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 So then, that's but here it certainly is like that. I'm sure that if we calculate for that, then will be this interaction. But of course, we can forget about the boundary part and take only centers kind of which are responsible for the interaction and interaction. But the boundaries are just commutative. This should be easy, I hope. Okay. So then, affine, then as you know, everybody knows the reflection. You know, reflection is a mirror, and the ray is coming here, yeah, and then it's reflected. And we know this the law of reflection. Yeah, I mean, not to recall it because you know very well. Of course, if there is an object, then this object is real. Then reflected is some imaginary, and so on. Then you know very well. It's a question. What is that? There is also reflection in affine geometry. You know about it. So, for example, here, a reflection of the point in that point is symmetry. This is transformation. But if you perturb this cycle like before, you have only center symmetry set. So how does it look like reflection? This reflection, you take the point and reflect in that point and in it. It was not mistake, but it was so much simplified that it's invisible proper definition. The proper definition is different. I show you in a moment how to define, how to reflect the point of this and that set, not in the point. So, for example, the mirror here is like this mirror. So mirror might be also two-dimensional. We know using mirrors, but that means that that's. But here the mirror is that one. Mirror was here, point. But after perturbation, mirror is complicated. So this question, how this points of the anything of all points, I mean, really reflects in such strange mirror. They reflect. Oh, in here, if you take the point as a source of lines, because usually in optics you have the source of rays, optical rays, yeah, and then you have they reflects and you get the image. So then here you have the point, and if you have the all lines ray going through, that's an image of this point, you get some set. But of course, the reflection is in that set. Oh, and that's a construction, very simple construction. You take the point P as a, which one you prefer? I mean, this one. We have a point through which we send all rays. So then one ray is here. So you take the parallel line here, parallel line to there, and you find parallel line to that one. So this is that one, and parallel line to that, which is that one. So these are these dotted lines joining, and then you join these 2 points. And the reflected ray at that point, affine reflected, is the red point, red line. So if you do this, for example, for ellipse, where the point center symmetry of ellipse is that point, then you get the point which is just reflected in usual way. I mean, you put the distance like here, and then you take this distance here, and you get the p prime. P is reflected in this way. So the all lines passing through that point, they reflect in the line by this construction and pass through new point. Okay. Yeah. And then, of course, if you have a point somewhere here, then you see what you have to do. This is the rays lines passing through that way are not visible. So you see what's here. It's very interesting. And there's other examples. So slightly deformed ellipse, and then if we have such complicated object, then the center symmetry set is a blue one. You see, the blue one. And then if you take a point somewhere here, then its reflection is this red one. You see. And then what is important in singularity theory working, because this is that case, is that this calculations of this cast points, giving the this more advanced structures like swallowtails and so on. Here is in the center, you see. So the reflection is very similar to the center symmetry, say, very similar. And some other examples which showing the rays. This stuff. The rays. If the point is on the boundary, then of course its image is on the opposite side. Opposite side is on the parallel line. Yeah. Affine reflection from the side. If you have side and send all the lines tangent to the side, so you get very interesting object. Very interesting object. And then other constructions. I think that the other constructions, maybe this, yeah, I leave it for later because they are more complicated a bit. But now let's come to some summarizing and well, yeah. Oh, let me check on this what I already told. I repeat. Oh, so another symmetry. You see, this is also very important symmetry. So then it's related to symmetry. You have a body, it's a fish or something, and this is interesting, a kind of skeleton, affine skeleton of that, or affine structures of some symmetric structure. So, so the medial axes, which are just, you know, we have all of in us, we have a lot of axes of symmetry. So then you see, if you take the points, all points which are centers of the cycles, which are tangent to the boundary of the object. So they give you such curve. And then, of course, it's somewhere here, and then here. Yeah, so this is called symmetry sets. Symmetry, or maybe some let's connect it to symmetry, then center symmetry. And then so this is related to bilateral symmetry. For example, if the middle axis is a straight line, then the object is symmetric about the line. Yeah. So for example, here, so as in the case of the ellipse. In the case of the ellipse, you see, So you have these lines. Oh, this line. These are the cycles tangent to the ellipse. So ellipse has such axis, very strange axis of symmetry, set of symmetry. And then, oh, you see, this is just the this is optical problem. I mean, this is also symmetry. This is that symmetry set. You have the ellipse, and it's a initial wavefront. So you send it. This is a 0 time, and then it's moving. You see, it's moving. That's a moment. Oh, moving, and always distance is the same from the ellipse. So you see, this singular points are not marked. They're only in self-intersection. Oh, symmetry. Yeah. Yeah. There are many interesting variants which have affine invariants. Some based on conics also. This is a very nice subject of mathematics, believe me. It's not so restricted only to plane or to RT. This is quite universal and also very applicable. And then, for example, here, if you consider the area here, constant area, then you get also something like that. You take interval which give you the division onto two parts on the same area. So, for example, this is the area some 100 square centimeters or something, and then if you move that line, then always is the same area. So then you get an interesting set, singularity. This is completely different measure of something, of that curve, of that oval. No, this is just again the center symmetry set, which is defined like that. Oh, I see that these two lines are not so parallel. It seems me that this line is not drawn parallel to that. That's a mistake. Well, the program is not okay. And then, and this is should be okay. So the other situation where the parallel tangents, this is very important because we have this line. This is the move from affine wavefront movement. Yeah? So that, and if we suppose that the derivatives to this, to this surface are, are always tangent to the surface, and for a fixed lambda, this guy is tangent plane to that of its lambda, and then we have this situation. So then if this condition fulfilled, then the lines are parallel to the image. So this is just kind of definition of affine wavefront moving, wavefront transportation. So this is interesting. This is not Euclidean, like in optics, but Oh, this is the case of center symmetry set. You see how this oval is changing. It is from the cycle to the curve with this curve is the constant width. So there was a double cover. This is something. And there is some calculations, but of course, I will show some program how to I think that people can use the MATLAB or MyPool or Mathematica and make some investigations by yourself, and you can even find a completely new object, because this affine geometry is not very extended. You know, of course, you know that in mathematics, the complex analysis and geometry is in most in all directions, but also in some other directions. But so let me show you the something what you can construct. Yeah, I have to my lectures since many years. I used to have a laboratory, so I had people of computer science also who were providing the help for students to solve some problems graphically. I mean, because there is a problem, a mathematical problem, and this is possible to visualize it in some way. It's very helpful. In singularity theory, there is a lot of this type of things that we can visualize. So, not artificially, but truly calculated. So this is some project, and you see, oh, that's you can manipulate this, of course, to get this, and then maybe we have what we want: center symmetry set. Center symmetry set looks like that, you see. And then, well, of course, maybe the more points. The more points. Oh, so more points. The center symmetry set looks like that. And of course, if you can complicate this a bit, or if you curve a lot, then it's big one. If it's similar to the cycle, smaller and smaller. You become smaller and smaller. Oh, oh. So you see, why is difficult to say, but this is mathematics. This is the shape which we didn't our eyes not see, but our brain, our mind is seeing. But even more complicated. But I can. So this is center symmetry set. Yeah, of course. This, yeah, it's, it depends on the shape. If this is very curved, you see, then this is close. It's a big one. And now you can take this caustic, the dual Wigner caustic. Oh, you see, maybe more points. These points should be seen here, but I don't know why they don't. Maybe no. Because I change the number of points which we computer use to calculate. I don't know how many of them. So this is the dual set. Dual set, from other point of view, it's more strict. I mean, it's less structure in some sense. You see, here is this swallowtail, but the dual set is not so complicated. Very strange. That I don't understand why. You see, this is just the triangle kind of, and this is already swallowtail points, and so on. It's very strange. So in some sense, this set, dual set, looks for these flats more than for these curved objects. These curved objects here have more structures. Very interesting. Very interesting. And then, of course, we can also display something like here maybe take it off, and then the lines normal curve. Ooh, this is so because maybe this is so complicated because you see the curve, the red curve is in big parts is very flat. So there's a lot of these lines which are parallel points. E lambda set. Lambda set for lambda, it depends on lambda. Lambda is perhaps 0 here, so then if we take lambda, say 0.6, it's like that. You see lambda set. Lambda set. Well, very interesting, but it is moving on that complicated center symmetry. For lambda 0.6, if I take 0.5, then will be just Green-Cost. But if I take 4, then something like that. If I take 3, all this is less visible. Maybe 55 or 55. You see, well, something like that. And if we take the display, for example, lines normal. So this is lines to dense. No much. You see, these are normals. Normals to this, but Euclidean normals. So what's the difference between Euclidean and Affine? Euclidean normals give such pictures which are disappearing very quickly if you move if you change the viewpoint. So this is okay. This is tangent lines. Tangent lines to the curve. That's something natural. Now this line between tangent points. You see, they give, of course, the center symmetry set. But this is the lines which it's enveloped in this center symmetry set. And yeah, and then of course there is also a very nice manipulation of the distance. So we will take, this curve is here is really simple. Okay. In a more dimensional case, so this is interesting. How does look like this program in more dimension? So it is in, say, 3 dimensions. You know, this is the blue one, is the center symmetry set, and the black one, that is dual linear caustic. And this is the structure which is normally in V. Yeah, but that's something what is very important for using in modeling. Then I have some other calculations which I can. This is very, you see, this is some view from other sides of the case. In this 2-dimensional case, it's much more complicated to calculate. Really. But some people like to make it more complicated. I like it more, it's less complicated. Yeah. So then now maybe I tell you a bit more about some constructions of I forget how to say full screen here. Control L, but here. So yeah, and we came to affine constructions. Affine constructions which also give some new invariants for surfaces in R3 and R4. You will see that. So that is, for example, here, if you study some geometry, affine geometry, surfaces, which mathematician should investigate such? At least for making like each person, each human should make exercise. So, you know, run, sometimes make like that, you know. The same, do something in 3, 4 geometry. So, and, the contact. Yeah, contact is very important notion, and then also in affine geometry gives a new invariance, very important. So Monge form. Usually, if we have a surface, surfaces are maybe very complicated sometimes, you know. Then we don't draw it all, but there's some mathematician already introduced some method that you just take some tangent plane to the surface and take coordinates like that, and this is the Monge form. Monge form is just, you see, this is z, this is x, this is y, and this is the graph of a piece at each tangent plane in RT. That's the function. Z is a function of your x, y, and this is just a graph of this function in this surface. So this is what Monge form. And when you see, and now what we can do with that? This is very important from affine geometry. If you have 2 points like that, and then you reflect a piece of that surface in the center of that interval to the piece or to the surface on the next point. So this is P, this is P prime. I show the picture in a moment. So then we have 2 points, you see. We have 2 points, P and P prime, on the surface. And then we consider 2 points, you see. This is P and P prime, and then close. You take the close point S plus X, T plus Y, which is and then this Z is F on S plus X, T plus Y. And then you reflect this in in the center of this interval between P prime and P. This construction is not so complicated. I mean, it looks like, but in fact, no, but gives very interesting generating families, which says about the structure a lot. And then, of course, it reflects that point to here, which is calculated. I calculated it here. So midpoint, of course, midpoint. So center of this interval is here. Yeah. Oops. This is S plus U over 2 and plus V over 2, and then ST UV. That's also half of it. So this is the half of interval. And then reflected point, reflection. Then what is reflection? You take this vector, and then you take this vector and add to this vector -2 of that with this direction. So add that vector. And then this is just written here, this reflection at the point. This reflection. We got this one here. Why this is so important? Because when we get here, we get this surface, we send it here, then there are two pieces here. You see, there are like biscuits. You know, then you have this one, and you have maybe something like that, which is tangent somewhere to that. It is tangent, maybe not there, but maybe somewhere here. And then it's important the tangency of these two pieces. And that's just a very infinitesimal geometry. And then we call, we construct the contact function. You are a student, so you know that calculations are very important. So the contact function is a function. You see, the idea is very simple. Look, you have some, say, surface, and you have some other surface here, which is touching that surface somewhere at some point. And then this surface is parameterized by x as well. So it is two-dimensional, so maybe x, y, and it is f1 on xy, f2 on xy, and f3 on xy. Yeah, this is that surface. Usually parameterize such surface, in such way. And this one we give not by parameterization, but by function, as a zero of some function Singularity. So this surface is, say, just f on this is u v w equals 0. So this is just that function. And what's a tangent? How we investigate a tangency of these two functions? We just take the composition of this just two mappings. So mapping is, this one is R2 into R3, this mapping, and this mapping is R3, you see, into R, this one. So let's be this is, say, phi, and this is C. And then what we have, well, we just compose. You see, phi, C, phi, compose. You take R2 into R3, and then, if you compose this way, into C side. And then this is R2 into R. And all classes, equivalency classes of singularities of this mapping just classify the contact singularities, the contact classes of contact. So that's of course this is some theorem which we necessary to prove. So we construct this function. We construct this function. Oh, let's another. Oh, we construct this function here. Oh, like this is just the function, which has these two variables, S2, ST, UV, but UV are parameters. I mean, these are parameters, and XY is equal. This is the function which is the tangent contact function. Some contact, you see, the contact. How to just catch the contact. And that is singular at 0 if the tangent planes to this M and to P and P prime are parallel. And then of course we have this or the use of that very important use. We can investigate what surface of the points of the surface are parabolic or Morse points or other points and so on. So this is just the case. Another family of reflections which we are going also to use so that using the contact surface is just simple. You see, you have the surface, this is the black one, and then you choose the point, and then you just reflect at that point a piece of this the black surface. So you get the blue one. Seems very similar. No, but it's not exactly, but because this is reflected. Reflected. It's not the same, but reflected. So M star at the point PQR. And then you see how to reflect. So you take the P plus X, Q plus Y, R plus Z to that point somewhere, and well, this one, and you reflect, which is an M, and to reflect it at PQR. So how to find this point? And this is that point. But it's necessarily, I mean, it belongs to this reflector. And then it appears that contact of this object says a lot, or maybe everything almost, about the singularities of this black or black surface. So if you have surface and you want to investigate its structure, then this is just affine, not metric. You don't use metric. So you don't even use the Gauss curvature or some other things. Not so much structure like people sometimes need to do this. But you can say a lot about this singular points. Of course, some of them they are like in Euclidean geometry. So yeah. And then the contact functions for that. The contact function between M and M star at PQR. So this is maybe, you see, we have these points, we plug to that because this is, that is, oh, there's something should be 0 here. No 0. Should be 0. Okay, 0. 0 is 0. It means nothing. For Greeks was nothing. So let's forget nothing. But and then of course the contact function is written here, and just f is unfolding of symmetric functions. You see, and then in this way we come to the very complicated sometimes singularities. here there are singularities which are invariant according to change of sign of, reflection of some variables. So we call it symmetric functions. If you change x, y into minus x minus y, it's the same. And then singularity theory for such functions looks completely different. It's necessary to prove very complicated theorem again, theorems. So then, yeah, and then, so then we investigate something what is just always we hear this function, so-called bifurcation set. Bifurcation set is a set of such PQ that there exists xy, and this conditions fulfilled. Derivative according to x, derivative according to y, and this determinant of the second derivatives according to y. The Hessian matrix according to vector y is 0, and this is the set which says where there are points which are singular on the surface, very distinguished points. So this is the bifurcation sets are fundamental because this is the sets where they're branching. Our life is all the time branching. So each point of our time is a branching point. So only different kinds. So, and then we can find out some area of the surface of the n-dimensional surface of the curve where there are some interesting properties. And that's also written families of you see, this is the case. That's if you are interested in some calculations on that, then in R4, this is not much known about the geometry, affine even geometry of two-dimensional surface in 4 dimensions. Because in 3 dimensions, this is known much. There are books and so on, but in 5 also not, but in 4 not much. So, but the 4-dimensional space is just space-time. So this is quite important. Anyway, this is some you see, this is some surface of that of R4. 2-dimensional. Of course, maybe 3-dimensional, but it's 2-dimensional because 2-dimensional is something easier than 2-dimensional. And then we take the parameterization of this reflection. We reflect it. Parameterization of reflected is here. See, this is parameterization of the reflected surface. And the contact map. The contact map here is the mapping of R2 into R2, preserving 0. So mappings R2 into R2, we have very well classified singularities. In fact, today we have classified singularities of all mappings, almost. So this is just the contact map, and in classifying and investigating singularities of this map, we know just the structure of this manifold or this surface. And this is just the bifurcation set, which is the fundamental here. So where the surface has the singularities. But here we have R2 into R2. So then this stability. We investigate stability of this mapping. Let's see if it's unstable at xy, then this is the point, and this point is just the bifurcation point. And there's some papers you can look through to if you are interested if you are interested in concrete calculations, then you can find that. Of course, I was just roughly. And then I know that you are tired. Maybe we can take a break. Because next time, because now we have a 10 minutes. So let me. We finish or not? Yeah. Thank you very much. So tomorrow we say about symmetry. Also. What? Not invisible.
It can be
Too dark.
And they suppose there will be a break. They will be not.
We should make break, but if you let me know, then I could stop. But I
have a break.
absolutely we make a break.
That's fine.
Yeah.
There are some people all online. I don't know.
Tomorrow will be even nicer. Oh, I don't know, it's nicer, but there are many pictures also, which are important. I mean, pictures. Okay. I can imagine that some things are maybe they have questions. Some questions. See you guys tomorrow. Yeah, tomorrow.